So in this video we'll discuss about the conjugate beam method to determine the deflection and rotation at given or at a particular point. So for this let me take a beam. So simply supported beam, if I'm taking AB, okay, and a point load P acting at a midspan L/2 L/2. Okay, so this is the given criteria. Then the bending moment diagram for this will be okay. So this will be the bending moment diagram for the simply supported beam with a point load at the midspan, and the magnitude of this point will be WL/4. So this is the bending moment diagram for that given simply supported beam. Now the main point or main step in conjugate beam method is to convert this bending moment diagram to M/EI diagram. Okay, for this what we do is we have to divide the magnitude by EI, then we'll get the required M/EI diagram. So this span is divided by EI given for that member. For example, in this case, if I am provided with EI for this span, then the M/EI diagram will be somehow like this. Okay, so this is the M/EI diagram. Now after plotting this M/EI diagram, the step for conjugate beam method is nearly completed. So in this method what we do is, so if this, in this case this is positive, so the magnitude of loading of M/EI diagram, so this actually is a conjugate beam. Okay, this is the real beam and this is the conjugate beam. So the magnitude of loading in conjugate beam is obtained by dividing the bending or moment of that beam by the EI value of that portion. So WL/4 EI. So this will be the M/EI diagram, that is the conjugate beam. Now with this magnitude of loading, we can calculate the shear force at A and shear force at B, that is VA and VB, and VA is equal to VB is the rotation of real beam. Okay, so the main point here to understand is that the shear at any point on the conjugate beam is equal to the slope of the corresponding point on the real beam. Okay, and the moment in the same case, if the moment at any point on the conjugate beam is equal to the deflection at the corresponding point on the real beam. So this is the basic concept you have to understand from this conjugate beam method to solve any problem. So the moment at any point on the conjugate beam is equal to the deflection of the corresponding point. So these two are the theorem that we should understand to solve using conjugate beam method. So these 2 points you have to understand. And another point to understand here in conjugate beam method is the conversion of the supports from real beam to conjugate beam. For example, this is a hinged support, this is a simply supported support, this is a fixed end support. So this is the real beam. Okay, real beam conditions. Now if I have to convert this into conjugate beam, as we have already seen, the hinge support is hinge support in case of conjugate beam, the roller support is roller support in case of conjugate beam also. So conjugate beam So this is the condition, okay, that is it remains same, and this will also remain same. But in case of fixed support, this changes into a free end support, okay, free end support, and vice versa. That is, a free end support will be converted into a fixed support in case of conjugate beam, okay. That is, if a free support is provided in real beam, it will change into a fixed support in case of conjugate beam. And similarly, if we are provided with a overhanging portion, for example like this, then it is converted into a internal hinge, okay, and a internal hinge will be provided into a, or it will be converted into a overhanging portion. So this is the general procedure you have to understand before solving conjugate beam method, these two theorems and this process of converting from real beam to conjugate beam. So let's move into a numerical now. So the questions asks us to determine the rotation at A and deflection at C, okay. So as we have already discussed here, we have to find the shear force and bending moment which will be equivalent to the rotation and deflection respectively. So in this question there is a simply supported beam AB and a overhanging portion BC. The flexural rigidity is 2 and BC, that is the moment of inertia, is 1 over here, and 2 EI and EI. The span is 6 meter for AB and 3 meter for BC. A point load is acting at the mid span of AB 80 kilonewton, and BC, and a 20 kilonewton force is acting at the free end of the beam. So to solve this question, we have to split the given beam into two parts, so it will be easier us to solve. So splitting it into two parts, a hinge over here and a roller in this part. Splitting is done in case of that the load at overhanging portion is not included for first part, and the loading at the simply supported part is not considered in the second part. So in this case I will be considering the loading at simply supported beam only, that is 80 kilonewton. A, B, C, plus the combined effect of the two beam will be considered. So this is the case, and we are provided with 20 kilonewton at the free end. So this is the given condition. If we see A, B, C, so there are provided with the loads 80 kilonewton and 20 kilonewton, and we have support at AB. So we have to determine the support reaction. So for the first part, 80 kilonewton acting at the mid span, so we can clearly say the load will be, or the support reaction will be 40 kilonewton acting upward, because the point load is at the mid span. So 40 kilonewton from the A and 40 kilonewton from the B will equally support the coming load. In case of A, B and C, the load is acting at the far end, so we will take moment about A to determine the reaction at point B, and applying the equilibrium condition of vertical force, we can calculate sigma, we can calculate the reaction at A. So 20 kilonewton at taking moment about A is equal to 0, the distance is 6 meter, and it will be 20 multiplied by 9 minus there is no any other forces, so 20 into 9 divided by this distance 6, so it will be 30 kilonewton, okay. 30 kilonewton load acting vertically upward. Now 30 upward, 20 downward, so 30 minus 20, it will give me 10, so the force acting will be 10 kilonewton, okay. So this is the support reaction calculated for this step. Now, as I have said, with this we can draw the BMD, and with BMD and taking the EI value, we can draw the conjugate beam with M by EI loading. Okay, so what we do is we have to combine this two beam mechanism and draw the combined conjugate beam. So taking this two 80 kilonewton, and for this case the formula for bending moment is equal to WL by 4, okay, for point load at the mid span. So if I write this A, B and C, so 80 kilonewton, 80 multiplied by length 6 meter, okay, 80 multiplied by 6 meter divided by 4, this is 120, okay, 120 EI. This point will be 120 by EI, but the moment of inertia for this value, for this member is 2, so we have to divide by, that is, let me draw it, okay, so 120 by 2 EI, that gives me 60 by EI, and it is positive, so the load will be acting, or the loading will be downward. So this is for AB portion. Now from this figure we can see there is another type of loading also. So you can do, this point is a hinge support, so it will have a moment 0, it is an obvious fact, but this B is an intermediate support, so it will have a moment, and the moment will be equivalent to 10 multiplied by 6, okay, 10 multiplied by 6, the 10 multiplied by 6, okay, that is 60 by 2 EI, that gives me 30 EI, okay, but the same load will be acting on this portion also, so it will be extended up to 60 by EI. For this portion BC, it has moment of inertia 1, so 60 by EI, and this portion will have a 0 moment, so, and in case this is a conjugate beam, so the free end will be converted into a, yes, will be converted into a fixed support. So let us consider the moment to be MC, okay. Now this is negative, so the force will be acting vertically upward. So this is the conjugate beam with M by EI loading, okay. So with this we have the loading through which we can calculate the shear force and bending moment to determine the rotation and deflection. So let us suppose VA and VB be the upward reaction, okay, upward reaction at A and B. So A and B, then if we take moment about the left portion of A only, okay, if we see the left portion of B only, taking moment about left portion of B only in the conjugate beam, okay, in the conjugate beam. So here what we have to do is that VA we have there, So VA multiplied by 6, the span, and there is the triangular loading of 30 by EI. So what we do is the triangular loading is computed. So 1 by 2 multiplied by 30 by EI multiplied by this distance, that is 6 meter, multiplied by 1 by 3 from the so 1 by 2 into 60 by EI into 6 into 3, the half. Okay, uh, we will get VA is equal to 60 into 6 into 3 minus 0.5 into 30 into 6, 60. Okay, so VA is equal to 60 by EI acting vertically upward. So we have obtained the shear force at A, and according to the first theorem of conjugate beam method, the shear force at the point is equal to the rotation of that point. So the shear force of the conjugate beam at that point is equal to the rotation at that point in real beam. So rotation, or we can say slope, at A is equal to 60 by EI clockwise. So the sign convention is, if the shear force is vertically up, then the slope is clockwise. This deflection at C, and according to the theorem of conjugate beam method, the deflection is equivalent to the bending moment of the conjugate beam. So taking moment about C, okay, taking moment about C, so taking moment about C in this conjugate beam, VA multiply by, this is 6, this is 3, so total distance 9. It will be giving anti-clockwise, so minus 1 by 2 60 by EI into distance is 6 multiply by the half span of the given loading, that is 3, plus this distance is 3. So per this portion, again a triangular portion, so 1 by 2 30 by EI, 30 by EI, sorry, I have 30 by EI, the distance, okay, 30 by EI, the distance is 6 meter again, and the span is triangular loading, so 1 by 3 multiply by, from the base, okay, so from the base, so it is 1 by 3 multiply by the span, that is 6, plus the remaining portion 3. Again for the 60 by EI kilo loading, 1 by 2, again a triangular loading, so 1 by 2 60 by EI multiply by this 60 by EI is for the right portion, so the span is 3 meter and acting from towards the apex, okay, so 2 by 3 multiply by the span 3 minus, I'm taking this anti-clockwise, so MC is equal to 0, okay, because we have to find the moment at point C in order to determine the deflection. Now calculate this, okay, VA is equal to 60 by EI, 60 into 9 minus 1 by 2 60 into 6 into 6 plus 1 by 2 is 0.5 multiplied with 30 into 6 into 1 by 3, that is 2 3 2 plus 3 2 plus 3 plus 1 by 2 multiplied by 60 into 3 into 2. So this gives me 90. Okay, so MC going to that part, and then we get 90 by EI anti-clockwise, because our assumption was anti-clockwise, so we have got positive result, so our assumption was right. And an anti-clockwise moment suggests that the deflection, okay, the deflection at C is equal to 90 by EI downward. Okay, so this is the way how we can solve a beam using a conjugate beam method. I hope you have understood this process. Do subscribe us and like us on Facebook. What can be done is this conjugate beam can be simplified with the simple structure also. For this, what we have to do is, this is the given loading at the upper section. This will be acting vertically downward, and as we know, the magnitude is given by the area of the diagram. So the area can be calculated as 1 by 2, as it is a triangle, into 60, that is the height, into span, that is 6. So it will be 180. 180 by EI will be the magnitude of load, and it will be acting from at a certain distance. It will be acting at a certain distance. So for the point of action, it is a symmetric, so it will be at the mid span, that is 3 meter. Okay, so at 3 meter, 180 by EI loading will be acting. This is 3 meter. Now for another, this is the downward triangle for 30 by EI. So for 30 by EI, again we have to calculate area for the loading. 1 by 2 into 30, span is 6 meter. So 90 by EI will be the magnitude of point load, and the distance at which it will be acting can be calculated as from the apex. So 2 by 3rd of the span, that is 2 into 6 by 3, that gives me 4 meters. So at 4 meters somewhere in AB portion, 90 kilonewton, that is 90 by EI, will be acting. Okay, it is vertically upward, so in this direction. Similarly for this portion, it is also a triangle. The area can be calculated, 0.5 multiplied by height is 60, span is 3 meter, so 90 kilonewton, and the distance that will be at which it will be acting is from the C. I'm taking from C, so it is an apex. So 2 by 3rd of this span, that is 2 into 3 by 3, that gives me 2 meter. So at somewhere 2 meter, point load of, that is 90 by EI, will be acting. So 90 by EI at this point. Then again you can calculate the same process, sigma MB, with this. It will be much more simple to calculate this. For if I have to calculate the moment at the left portion of B, then 180 by EI into 3 meter, okay, 3 meter minus 90 by EI into 2 meter. So this will give me VA. So divided by 6, that is total span 6 meter. So in this way it can be done. Okay.